Polynomials. So we're venturing into territory where we're going to want to understand eigenvalues better. And it turns out that one of the concepts that will allow us to calculate eigenvalues is the theory of polynomials. So I figured it'd be best for us to do a complete lesson on polynomials separate from the matrix theory so that we can understand how this theory fits in later. So let's start with the basics here. So what is a polynomial? Well, for us, a polynomial in a variable t is an expression f of t that looks like this. F of t equals some scalar c sub n multiplied by t to the n plus another scalar c sub n minus 1 times t to the n minus 1. And we continue in this fashion, decreasing the power of t by 1 each time, and multiplying by a scalar by the next power down, until we get to the last two terms, which would be c sub 1 times t plus c sub 0. So this number n, which is the highest power of t here, is called the degree of the polynomial. And we call a polynomial monic if the leading coefficient, so the coefficient of t to the n, is equal to 1. So let's look at some examples. So a polynomial with degree 2 is typically referred to as a quadratic polynomial. So here we have an example. This one is t squared minus 2 times t plus 3. So the degree here is 2 because 2 is the highest power of t in our expression for the polynomial. This polynomial happens to be monic because the coefficient of t squared equals 1 here. Here's another example. So a polynomial of degree 3 is typically referred to as a cubic. The expression for this polynomial is negative 5t cubed plus 6t squared minus t plus 5. And this polynomial is not monic because the leading coefficient here is negative 5, which is not equal to 1. A polynomial of degree 4 is called a quartic. This one is 7t to the 4th plus 3t squared minus t. The leading coefficient here is 7, which is not equal to 1. So this example is not monic. And a polynomial of degree 5 is called a quintic polynomial. This one is the example given by t to the 5th plus t to the 4th plus t cubed plus t squared plus t plus 1. This is a monic polynomial because the leading coefficient is equal to 1. So here we have a bunch of different examples of polynomials. This sort of is an exercise intended to acquaint us with the language of degree and whether or not a polynomial is monic. So one thing to point out here is sometimes our polynomials have real coefficients, and sometimes they have complex coefficients that aren't necessarily real. We write f belongs to r bracket t if the coefficients of the polynomial are real numbers, and we write f belongs to c bracket t if the coefficients are complex numbers. So here's an example of a quadratic, 2t squared plus 7t minus 5. Here we would write f belongs to rt and f belongs to ct because every coefficient here is real, and remember that every real number is also complex. Here is another example of a quadratic. This is g of t equals t squared plus quantity 6 minus 4it minus the quantity 1 plus I. This is an example of a polynomial whose coefficients are complex, but they're not all necessarily real. So here we would say that g does not belong to rt, but g does belong to ct. One thing that is interesting about polynomials with real coefficients is that if we plug in a number and then conjugate that number into the polynomial, that's the same thing as plugging in the original number and then conjugating the entire polynomial. So f of the conjugate is the same thing as f of the number all conjugate. Now, when people study polynomials, they often care about the roots of the polynomial. So a root of a polynomial is a scalar r that you can plug into the polynomial to produce the number 0. So here we have an example of a cubic, t cubed minus 2t squared plus t minus 2. Well, when I plug in the number I into this polynomial, the output is equal to 0. So here we would say that r equals I is a root of this polynomial. Also, when I plug in the number 2 into the polynomial, we get 0 as the output. So r equals 2 is a root. On the other hand, if we plug in 1 into the polynomial, we produce the number negative 2, which is not 0. So the number 1 is not a root of this polynomial. So to verify whether or not a number is a root, we plug the number in and check if we get 0. Now, one thing to point out is that every root of a polynomial is a complex number, but some roots might not be real numbers. One theorem that we have is a theorem that says if our polynomial has real coefficients, then its roots occur in conjugate pairs. So if our polynomial has real coefficients and little r is a root, then the conjugate of little r is also a root. And the proof here really just hinges on the fact that plugging in the conjugate of a number into a polynomial with real coefficients is the same thing as plugging in the original number and then taking the conjugate. So f of the conjugate is equal to f of r conjugate, but if r is a root, that means f of r is 0, and the conjugate of 0 is just 0.